So we'll continue to make these points in a heuristic sense with simple equations and illustrate the concepts. So let's go ahead and see how we would compute the available potential energy. So you start with this simple setup where you have somehow created this slope in the density surface. So you have a light fluid on top of a dense fluid. And to create this, obviously you need some sort of energy input. Okay, so if you release the interface, the wedge of heavy fluid above this equilibrium line would come down, and this light fluid that is below the equilibrium line would go up. Okay, so let's say this angle is gamma. Why are we doing that? You can probably already think of Margulies' relation with two densities and a sloping interface, right? Front, we called it, right? So if you just release it, the final state will be that the lighter fluid would have gone up, heavier fluid would have come down, and you would have basically flattened the interface and create a stable situation where the heavy fluid is lying below the light fluid. What is happening here? There is no rotation, so it is just somehow create a slope and release it. Boom, you got a stable situation. Obviously Earth means a rotating planet, so we will have to figure out how this kind of an interface would work in a rotating fluid. Okay, so we can do the energy calculations with this setup. The slope here, hy, is approximated as 1/2 h, which is the total height, plus a perturbation, which is just gamma y, if gamma is small enough, right? We get rid of the sign in the multiplication here because it is small enough. So y is this direction in the horizontal. Okay, so for simplicity we constrain the slope to be small enough so that it doesn't hit either the bottom or the top. Simple enough. The center of mass gets lowered when you let the interface go and the final state of stability with the horizontal interface between the heavier and lighter fluid is accomplished. So the P has been released. Okay, the initial state had available potential energy, obviously, because you had heavier fluid above the equilibrium line and lighter fluid below the equilibrium line. Okay, now let's look at a simple way to calculate the available potential energy for this simple situation we have created. So two-layer fluid again with our hy of 1/2 h plus gamma y. Potential energy of the system is, in this case, okay, integrating from this end to this end and from bottom to top, 0 to h minus L to L, g rho z dy dz, where rho is the density gradient, and that goes simplifies into minus L or minus L to L dy, this direction, and 0 to hy, rho 2 z dz, and hy to h, so you are going from here to here and here to there, rho 1 gdz, right? So you have rho 1 and rho 2, that is the horizontal distribution is giving you the potential energy. That's a very simple equation. I hope you understand. Rho 2 is here. We're going from 0 to hy, rho 2z, rho 2z dz. How much potential energy is created by moving down some of the rho 2, and hy to h from here to there, how much potential energy is created by moving the heavy fluid up. Okay, rho 1 z dz. You can go through this calculation, which is in the appendix. I won't spend too much time on it, but I think you can see what simple adjustments have been made. Basically, we are taking the difference of rho 2 and rho 1 as delta rho, and expressing rho 2 and rho 1 in terms of delta rho. Okay, so the equations are essentially the same, and we have just reorganized it. So I'm just going to focus on this expression here. You have one term g h squared L rho 1 plus g delta rho over 2 minus L to L h squared y dy. So this is the kind of a perturbation to the potential energy when you move the equilibrium interface. You tilt it this way or that way, it doesn't matter. You create a additional source of potential energy, right? So g h squared L rho 1 is basically kind of the base potential energy. So going back to our expression of P equals G integral G rho dV, this looks like minus 0 to H minus L to L G rho Z dy dZ for our tank that we are looking at, right? So rho has a vertical distribution. So the previous expression can be simplified to h squared L rho 1 times G plus G prime over 4. You now remember your old favorite G prime, plus 1/3 rho 1 G prime gamma squared L cube. The thing to note here is that there is no H here. Okay, there is an H here, the mean potential energy, and then there is a additional potential energy which is independent of the height. It just depends on the tilt of the interface between the lighter fluid and the heavier fluid. G prime, of course, is our reduced gravity, rho 1 minus rho 2 divided by rho 1. Rho 1 is heavier than rho 2. So available potential energy in this case is the minimum potential energy, which I call the base potential energy. So when the interface is flat, there is potential energy, but it is minimum. It is at its minimum. You cannot lower it anymore in this two-layer fluid system. This is the basic minimum, right? So if you subtract the minimum from the total, you end up with available potential energy expression of 1/3 rho 1 G prime gamma squared L cube. This is an ideal situation, so just make sure you understand the concept. By tilting the interface between a vertically distributed fluid, APE is created, available potential energy is created, and it is independent of the height of the system. Right? The whole system is from the bottom to the top. What are we going to do with it? We're going to see how this will work in a rotating system. In this simple non-rotating system, if you created a tilt and you let it go, it's going to just slosh back and achieve minimum potential energy. Right? The sloshing may go on, create some waves, but eventually the energy is lost to friction. Kinetic energy is lost to friction, and you create back to minimum potential energy when the interface between the two is perfectly horizontal. Simple. What will happen when there is rotation? That's the interesting part we must learn for atmospheric general circulation model, general circulation being created by release of potential energy.